In this video, we'll go over why labs might use a single standard curve fit across multiple plates and how a bridge standard and QC sample can be used to normalize and verify acceptability. In many ELISA workflows, especially when running large batches across multiple plates, a full standard curve on each plate can consume a large number of wells and a significant amount of standard and reagent material. This can be a problem when standards and reagents are expensive, limited in volume, difficult to prepare, or when plate space should be prioritized for unknown samples. One way to reduce standard and reagent consumption is to run the full calibration curve on the first plate, then use a bridge standard and quality control sample on subsequent plates. This approach allows users to apply the 4PL curve from the full curve plate to other plates, while ensuring that each additional plate is performing acceptably. A 4PL curve has 4 parameters: the upper asymptote, lower asymptote, inflection point, and slope, and requires at least 4 usable standards to return a valid curve fit. Because of this, it's not possible to create a new 4PL curve using only the bridge standard. So the bridge standard is not used to create a new curve. Instead, the full standard curve from the first plate is treated as the reference curve, and the bridge standard on each later plate is used to adjust that plate back to the reference response scale. This method can be thought of as a curve transfer approach. The first plate contains the full calibration series and is used to fit the 4PL model. This provides the reference curve. Each subsequent plate includes a bridge standard at a known concentration. The expected response for that bridge concentration is calculated from the reference 4PL curve. The observed bridge response on the later plate is then compared with the expected response. The difference between the expected and observed bridge response is used to calculate a plate normalization factor. This factor is applied to the sample responses on the same plate before the concentrations are interpolated from the 4PL curve. A typical plate setup might look like this. The first plate contains the full standard curve. This could have a different number of standard samples and replicates depending on the assay design. These standards are used to fit the 4PL model. The first plate can also contain a blank sample, unknown samples, and a QC sample. On each later plate, the layout will include, at a minimum, a blank sample, bridge standard, QC sample, and unknowns. The blank sample is important because it allows each plate's background signal to be accounted for. The bridge standard supports response scaling or normalization between each plate and the reference curve. The QC sample is independent of the bridge standard. It should not be used to create the correction or normalization factor. Instead, it's used to confirm that the bridged calculation is producing acceptable results on that plate. The bridge standard should be selected from the informative part of the curve, often near the middle of the range or close to the EC50 region. Avoid choosing a bridge standard that is too close to the lower or upper asymptote of the curve. In those regions, the response changes very little with concentration, so a small measurement difference can produce unstable corrections. A good bridge standard is one that gives a consistent, measurable response and is close to the concentration range where many of the unknown samples are expected to fall. The analysis workflow has several steps. First, the 4PL curve is fit using the complete standard series from the first plate. The 4PL equation is d plus a minus d over 1 plus x over c raised to the power of b, where x is the concentration, y is the response, a and d are the asymptotes, c is the inflection point, and b is Hill's slope. Next, use the known concentration of the bridge standard to calculate its expected response from the 4PL curve. Then measure the bridge standard on the later plate. After blank correction, compare the expected bridge response with the observed bridge response. This gives the plate normalization factor. The sample responses on that plate are then multiplied by this normalization factor. The adjusted sample response is then interpolated from the 4PL curve from the first plate. And finally, the QC on the plate is calculated in the same way, comparing the obtained QC concentrations from the subsequent plates to the QC concentration on the first plate. If the QC result meets the predefined acceptance criteria, the plate can be accepted according to the user's protocol. Now let's look at a simple example. The bridge standard's known concentration is 100 picograms per milliliter. From the full 4PL curve on plate 1, the expected response at 100 picograms per milliliter is 1 OD. On plate 2, the same bridge standard gives a measured response of 0.9 OD. The normalization factor is therefore 1 divided by 0.9, which is 1.111. A sample on plate 2 has a measured OD of 0.45. After applying the normalization factor, 0.45 times 1.111, the normalized or scaled OD is 0.5. The value 0.5 is interpolated from the original plate 1 4PL curve to calculate the sample concentration. The QC is critical because the bridge standard alone only supports the normalization factor. It does not prove that the 4PL curve shape has remained unchanged on the later plate. The QC provides an independent check. It is calculated using the same bridged curve workflow as the samples. The QC sample is compared against the predetermined criteria, and if the result falls within the acceptance limits, this supports accepting the plate. If the QC fails, the plate should be reviewed or rejected according to the assay protocol. Acceptance thresholds should be defined by the user's validation requirements, internal procedures, or regulatory expectations where applicable. Including a blank on each plate is strongly recommended. Background signal can vary between plates. Without a plate-specific blank or zero, it can be difficult to separate true signal differences from background differences. By blank correcting each plate first, the blank helps account for plate-specific offset. The bridge standard can then be used to support response scaling between the later plate and the plate containing the reference curve. Keep in mind that while this technique is useful, it has its limitations. A single bridge standard can support a simple plate-level correction, such as response scale differences between plates. However, it cannot independently confirm the 4PL curve shape is identical on each plate. For this reason, the method should be qualified before routine use. Users should compare the reduced standard workflow against the conventional full curve workflow across representative runs and confirm that the sample concentrations and QC recoveries remain equivalent within predefined acceptance limits. Before adopting this bridge standard workflow routinely, it should be qualified and validated. A practical way to do this is to run several batches using full standard curves on each plate, then reprocess the data as if the later plates had only used the bridge standard and QC. Compare the concentrations from the full curve approach with the concentrations from the bridged approach. The run should be evaluated for bias, precision, QC recovery, and performance across low, mid, and high concentration ranges. Once the approach has been validated, the workflow, bridge standard concentration, QC rules, plate layout, and acceptance criteria should be documented in the assay protocol. Acceptance limits, QC rules, and suitability of this approach should be defined by the user based on their assay validation requirements, internal procedures, and intended use. For regulated studies, users should ensure the workflow meets applicable validation and reporting requirements. The fixed curve and bridge standard approach can be a useful way to reduce standard and reagent consumption, save plate space, and support larger multiple plate ELISA batches. The key point is that subsequent plates are not fitted with a new 4PL curve from the bridge standard. Instead, the full calibration curve from the first plate is retained, and the bridge standard is used to normalize each additional plate back to that reference curve. With an appropriate blank, bridge standard, QC sample, predefined control rules, and method qualification, this workflow can provide a practical way to manage multiple plate ELISA analysis while optimizing plate and reagent usage for the maximum number of unknowns measured. If you'd like to perform this workflow, we have a number of tools available for you, including a pre-configured MyAssays desktop protocol to run this workflow offline with your reader, or an online tool at myassays2.com. You can find these resources at the links appearing on screen now. If you need help integrating or refining this workflow to meet your own specific needs, please contact us at support@myassays.com.